comet doesn't choose where it points. It can't. The laws of physics decide that the moment it forms, 4.5 billion years ago in some distant stellar nursery, solar radiation pushes the tail one way, gravity pulls another, rotation, outgassing. The gentle pressure of starlight, these forces write the comet's story without asking permission. But on October 17th, 2025, something happened to interstellar object 3I Atlas that violates that script. Between September and mid-October, this 33 billion-ton visitor from beyond our solar system reversed the direction of its jets, not gradually, deliberately. Like something woke up inside it and decided the old program wasn't working anymore. Before we dive into what that reversal means for us, for science, and possibly for our understanding of whether we're alone in this galaxy, do me a favour. Hit that like button if you're ready to question everything you thought you knew about comets. Drop a comment telling me if you think we're witnessing natural physics or something engineered, and subscribe, because what happens in the next 2 weeks might rewrite textbooks, or it might change humanity's place in the cosmos. You don't want to miss either outcome. On July 21st, 2025, the Hubble Space Telescope captured an image of 3I Atlas that looked exactly like what you'd expect from a comet approaching the Sun. The tail stretched away from our star in a graceful arc, pushed by solar radiation pressure like a cosmic windsock pointing downwind. Dust particles, liberated from the nucleus by sublimating ice, caught sunlight and scattered it back toward Earth in that familiar fan shape. The jets, those focused streams of gas and dust erupting from active regions on the comet's surface, were doing what jets always do. They pointed roughly sunward, driven by the heat of our star vaporizing frozen volatiles beneath the surface. Everything was textbook. Everything made sense. Then came August. The Nordic Optical Telescope in the Canary Islands began tracking 3I Atlas more intensively as it crossed the 3 astronomical unit mark, entering the region where water ice begins to wake up and join the show. Observers noticed something odd in the September data. The tail structure was changing, but not in the way thermal models predicted. By early October, multiple observation teams were comparing notes, and the pattern became undeniable. The jets had shifted orientation, not by a few degrees, not through some gentle rotation bringing new active regions into sunlight. They had reversed. When the October 17th images came through from multiple independent sources, Hubble again, the Nordic Optical Telescope, and several amateur networks coordinating through the International Astronomical Union's Central Bureau, the conclusion was inescapable. The jets that had been pointing one direction for months were now pointing the opposite way. Imagine a car driving north suddenly driving south without turning around. That's the level of wrongness we're talking about. Comets don't do this. Now, before your mind jumps to malfunctioning spacecraft or observational errors, understand that we're talking about convergent evidence from different instruments, different teams, different methodologies, all arriving at the same conclusion. The Hubble images showed it. The Nordic Optical Telescope photometry confirmed it. Ground-based spectroscopy documented compositional changes coinciding with the transition. This wasn't a viewing angle trick or a processing artifact. Something physical happened to 3I Atlas between September and mid-October that fundamentally altered its outgassing pattern. Let me explain what jet reversal actually means, because the term sounds almost mystical, but the physics are concrete. A comet's jets are directional. They emerge from specific locations on the nucleus vents, essentially, where subsurface pressure builds up and breaches the surface. The direction those jets point is determined by the local surface topology, the rotation of the nucleus bringing different faces toward the Sun, and the thermal properties of the material. Once established, those jets don't just flip around. The nucleus would need to either rotate into an entirely different orientation, exposing previously dormant regions while shutting down previously active ones, or the physical structure of the active regions themselves would need to transform. But here's the thing. 3I Atlas has a rotation period of approximately 36 hours. We've been tracking that rotation photometrically, watching the brightness variations as different faces of the irregular nucleus catch sunlight. If the jet reversal were simply a matter of rotation bringing new vents into play, we'd have seen it coming gradually over multiple rotations. We'd have seen intermediate states, partial transitions, the old jets fading as new ones ramped up. We didn't. The transition was sharp, abrupt. Within a 2-week window, the dominant outgassing geometry inverted. Now, comets do sometimes show what are called anti-tails structures that appear to point toward the Sun instead of away from it. Comet Arend-Roland in 1957 displayed a spectacular anti-tail that confused observers until the geometry was understood. Comet Lulin in 2009 showed a similar feature, but these are projection effects. They happen when Earth passes through the comet's orbital plane, and we're looking edge-on at the dust sheet that the comet has been depositing along its orbit for months. From our perspective, that flat sheet of dust appears as a spike pointing back along the comet's trajectory, which might be sunward. It's an illusion, a trick of viewing geometry. The 3i Atlas situation is different. We're not talking about a temporary projection effect visible from one viewing angle. Multiple observers from different locations, tracking the object over weeks, documented an actual change in the physical emission pattern. Spectroscopy confirmed this wasn't just dust geometry, but active outgassing shifting direction. The coma brightness distribution changed. The dust production rate spiked during the transition. These are real physical phenomena, not optical illusions. The astronomical community's initial reaction was measured as it should be. Science doesn't sprint toward extraordinary conclusions. It walks. It checks its shoelaces. It asks whether the data might be wrong before asking whether physics is strange. Teams went back through their processing pipelines looking for systematic errors. They checked for instrumental artifacts. They compared calibration standards. They modelled every conceivable projection effect that might mimic a reversal without actually being one. And one by one, those mundane explanations fell away. The reversal was real. By late October, papers were being drafted. Modelling teams were running thermal simulations trying to reproduce the transition using purely natural mechanisms. The spectroscopy data from JWST became critical here, showing that the coma composition was dominated by carbon dioxide, about 87%, with water, carbon monoxide and carbonyl sulfide making up most of the remainder. That composition profile told a story. It suggested a comet that formed in the frigid outer regions of some distant stellar system, rich in the most volatile ices, structurally different from typical solar system comets. And those compositional differences might, just might, explain behaviour we'd never seen before simply because we'd never had an interstellar visitor quite like this one. But even as the natural explanations were being refined, 3 observations kept nagging at researchers who were paying close attention. 3 data points that didn't fit cleanly into any of the models being proposed. 3 pieces of evidence that suggested this wasn't just an unusual comet, doing unusual comet things within the boundaries of known physics, but something genuinely anomalous. Not necessarily artificial, let's be clear about that, but anomalous. Different. Requiring explanation. This wasn't supposed to happen. And the fact that it did means we're either learning something new about how interstellar comets behave under solar heating, or we're seeing something that challenges deeper assumptions about what comets are and how they work. Either way, the next steps in the investigation would determine which of those possibilities was real. Which brings us to the physics that governs every comet we've ever studied, the baseline against which 3i Atlas is being measured. To understand why the 3i Atlas jet reversal is so puzzling, you need to understand how comets work in the first place. And fortunately, the physics are elegant, even if the details get complex. At the most fundamental level, a comet is a dirty iceberg, not water ice exclusively, though water is usually the dominant volatile once you get close enough to the sun, but a mixture of frozen compounds. Water, carbon dioxide, carbon monoxide, methane, ammonia, more exotic organics, all glued together with dust, rock and carbonaceous material. This mixture formed billions of years ago in the cold outer regions of a stellar system, where temperatures were low enough for these volatiles to freeze solid. When a comet ventures into the inner solar system, solar radiation heats its surface. That heat doesn't just warm the ice, it drives a phase transition called sublimation, where solid ice converts directly to gas without passing through a liquid phase. Think of dry ice, which is frozen carbon dioxide. Leave it on your countertop and it doesn't melt into a puddle. It sublimates, turning straight from solid to gas, creating that eerie fog that rolls across surfaces. Comet ice does the same thing, but on a vastly larger scale and driven by the sun's energy instead of room temperature. Now here's where it gets interesting. Sublimation doesn't happen uniformly across a comet's surface. The nucleus isn't a smooth sphere of pure ice. It's irregular, lumpy, with varying composition from place to place. Some areas are richer in volatile ices, others are covered by a thick layer of refractory dust that insulates the ice beneath. The rotation of the nucleus brings different regions into sunlight at different times, And critically, different volatile species sublimate at different temperatures. Carbon dioxide ice begins to outgas vigorously around 3 to 4 astronomical units from the Sun, when surface temperatures are still well below the freezing point of water. Water ice doesn't really wake up until the comet crosses inside about 2 astronomical units, where temperatures climb high enough for significant water sublimation. When ice sublimates beneath the surface of a comet, the gas has to escape. It builds up pressure in the porous subsurface layers, percolating upward through cracks and voids until it finds a path to the vacuum of space. When it does, it erupts as a jet. Picture a pressure cooker releasing steam through its valve. That's essentially what's happening, though the physics are more complex because the expanding gas accelerates to supersonic speeds, cools adiabatically, and entrains dust particles as it escapes. Those dust grains, lifted by the gas flow, become visible when they scatter sunlight. That's what we see when we observe a comet's coma and tail. We're seeing sunlight reflecting off dust particles that were recently trapped beneath the surface and are now being blown into space by sublimating ice. Here's the critical point for understanding jets. They have direction. The gas escapes perpendicular to the local surface, or at least in whatever direction the subsurface venting structure permits. If you have an active region on the sunlit side of the nucleus, the jet erupts sunward, then gets swept back by radiation pressure and solar wind into the characteristic dust tail, pointing away from the Sun. The recoil from the jet, the rocket effect of mass being ejected at high velocity, exerts a tiny but measurable force on the nucleus itself. This is called non-gravitational acceleration, and it's why comet orbits are notoriously difficult to predict with high precision. The jets act like little thruster firings, nudging the nucleus in various directions depending on the geometry and timing of the outgassing. Because the nucleus is rotating, the jets turn on and off, sweeping through space like lighthouse beams as active regions rotate in and out of sunlight. Some comets have multiple jets operating simultaneously, creating complex coma structures with spirals, shells, and streamers visible in high-resolution images. The overall effect is that the coma, the cloud of gas and dust surrounding the nucleus, develops a characteristic shape determined by where the jets are, how strong they are, and how the solar wind and radiation pressure shape the outflowing material. Now, the tail, actually 2 tails typically. The dust tail is the bright sweeping arc most people picture when they think of comets. It's composed of dust particles that have been pushed by solar radiation pressure. Larger grains lag behind the comet's motion, creating a curved tail. Smaller grains are pushed harder and create straighter, more radial structures. The ion tail, less visible to the naked eye but prominent in certain wavelengths, is composed of ionized gas molecules stripped of electrons by solar UV radiation and then accelerated to enormous speeds by the solar wind's magnetic field. Ion tails always point directly away from the Sun, forming those beautiful straight blue streamers you see in long exposure photographs. The key takeaway is this: comet behavior is governed by solar heating, surface properties, rotation, and composition. These factors determine when jets turn on, where they point, how strong they are, and how the coma and tail develop. And while individual comets can be quirky, no 2 are exactly alike, they all follow the same underlying physics. They're predictable within a reasonable range of variation. Which is why the 3-eye atlas reversal is so jarring. The physics doesn't allow for jets to simply flip direction midstream unless something changes fundamentally. Either the active regions shut down, and entirely different ones activated possible but requiring explanation, or the composition of the outgassing material shifted so dramatically that it altered the jet mechanics also possible, but rarely observed so abruptly, or something about the nucleus itself changed in a way we don't typically see. Let me give you an analogy. Imagine a garden sprinkler. It shoots water in specific directions determined by the nozzle design and water pressure. If you suddenly see the sprinkler shooting water the opposite direction, you'd immediately ask, did the nozzle rotate? Did the water pressure reverse somehow? Did someone install a different nozzle? You wouldn't just shrug and say sprinklers do that sometimes, because they don't. There are physical constraints. The 3-eye atlas situation is similar. Jets have physical constraints. Reversing them requires a mechanism, and that mechanism, whatever it is what scientists are trying to identify. One hypothesis that immediately comes to mind involves compositional transitions. If a comet has layered structure, say, an outer shell rich in carbon dioxide ice surrounding an inner core richer in water ice, then as the Sun heats it progressively deeper, you might expect the dominant volatile to shift from CO2 to H2O. and because those species sublimate at different rates and have different molecular masses, the jet characteristics could change. CO2 jets, being from a lighter, more volatile molecule, might produce different thrust profiles than water jets. If the transition from CO2-dominated to water-dominated outgassing happened relatively quickly, you might see observable changes in jet behavior, and this is important, that kind of transition would typically manifest as jets ramping up or down in intensity, possibly with new jets forming as deeper layers activate. It wouldn't naturally produce a reversal of existing jets. To get a reversal, you'd need the new water-rich jets to preferentially form on the opposite side of the nucleus from where the old CO2 jets were most active. That's geometrically possible if the thermal wave penetrating into the nucleus encounters structural asymmetries, volatile concentration gradients, or buried icy layers with different distributions. It's possible, but it's not the default outcome. It requires specific conditions, specific internal structure, and specific timing. And that brings us to the competing hypotheses that are being debated right now in the astronomical community. The mainstream view, held by the majority of scientists tracking 3I Atlas, is that we're seeing a natural compositional transition playing out in a particularly dramatic way because of the object's interstellar origin and unusual internal structure. The minority view, advocated most prominently by Dr. Avi Loeb and a handful of colleagues, is that the observations don't fit natural models as cleanly as they should, and that we ought to seriously consider whether 3I Atlas might be displaying controlled behavior. Not definitely controlled. Loeb himself hedges with probability estimates, but controlled is a possibility that deserves rigorous testing rather than dismissal. So let's walk through the natural explanation first, giving it the strongest case possible, because that's what intellectual honesty requires. If the natural explanation works, then the mystery resolves, we learn something new about interstellar comets, and science proceeds. If it doesn't work, if the data keep resisting natural interpretation, then the alternative becomes more pressing. Either way, we need to understand what the baseline expectation is before we can evaluate how far from baseline 3I Atlas actually strayed. The leading natural explanation for 3I Atlas's jet reversal is rooted in composition and thermal physics. It goes like this. 3I Atlas formed in the outer regions of a stellar system that's not our own. Probably it coalesced in the debris disk surrounding a young star, or in the scattered population beyond that system's equivalent of the Kuiper belt. The temperatures there were so low, perhaps only a few tens of degrees above absolute zero, that even the most volatile substances froze solid. Carbon dioxide, which sublimes at 194 Kelvin at 1 atmosphere of pressure, and at much lower temperatures in vacuum, would have been locked into the ice matrix. Carbon monoxide, with an even lower sublimation temperature, would have been abundant. These ultravolatile species would dominate the composition, with water ice present but not necessarily the primary component. This is different from typical solar system comets, which formed in our own protoplanetary disk under conditions where water ice was the dominant volatile. Most comets we study, Jupiter family comets, Oort cloud comets, Kuiper belt objects, are water-rich because that's the environment they formed in, but an interstellar comet has no such constraint. It formed in a different system, under different conditions, possibly around a star of different mass and luminosity. Its composition reflects its origin. When 3I Atlas entered our solar system on its hyperbolic trajectory, it was initially very cold and very far from the Sun. As it began its inbound journey, crossing the 543 astronomical unit marks, solar radiation began to warm its surface. The first species to respond was carbon dioxide. Well before water ice would sublimate significantly, CO2 began outgassing. This early activity, dominated by carbon dioxide jets, is what observers saw during the summer of 2025. The spectroscopy data confirmed it. The coma was overwhelmingly CO2, roughly 87% by number density, with minor contributions from other species. But as the comet continued approaching the Sun, the thermal wave began penetrating deeper into the nucleus. The surface layers, now depleted of their most volatile ices, formed a crust of refractory material, dust and rock left behind after the ice sublimated away. Beneath that crust, deeper ice remained, insulated but gradually warming. And at some critical point, two things happened. First, the carbon dioxide in the near-surface layers became sufficiently depleted that CO2-driven jets began to weaken. Second, the deeper water-rich layers reached temperatures where water sublimation could drive vigorous outgassing. Now, Here's where the geometry comes into play. If the carbon dioxide was concentrated more heavily in certain regions of the nucleus, perhaps because of how the object formed, or because of previous heating events during its journey through interstellar space before entering our system, then the CO2 jets would have been strongest in those regions. When those regions depleted, those jets faded. Meanwhile, if water ice was more concentrated in different regions, or in deeper layers beneath areas that hadn't been as active during the CO2 phase, then the new water-driven jets would preferentially form in locations that were geometrically distinct from the old CO2 jets. The result? A reversal in the net direction of outgassing, not because individual jets physically flipped around, but because the ensemble of active regions shifted from one part of the nucleus to another part, with a different orientation relative to the Sun. From Earth, observing the integrated effect of all the jets together, it would look like the jets' reverse direction. This model is bolstered by the JWST spectroscopy. The James Webb Space Telescope, with its exquisite infrared sensitivity, observed 3I Atlas in late September and early October. The data showed exactly what the compositional transition model predicts: a coma still dominated by carbon dioxide, but with increasing contributions from water vapor and other species that become prominent closer to the Sun. The grain size distribution in the dust also shifted, consistent with a change in the sublimating volatile driving the dust entrainment. Smaller ice-coated grains, easily lifted by CO2 gas, gave way to larger refractory particles being lofted by the more energetic water sublimation. There's also the issue of scattering phase function, how dust particles scatter sunlight, depending on the observer's viewing angle relative to the Sun. When the dust grain population changes, the scattering changes. Some of the observed brightness variations during the transition period could be attributed to this effect. Forward scattering, where sunlight passes through the coma and dust scatters it toward Earth, enhances brightness in certain geometries. Backscattering, where light reflects directly back from the dust, dominates in other geometries. As the dust composition and grain size distribution evolved during the CO2 to water transition, the scattering properties evolved, potentially amplifying the apparent dramatic nature of the changes. Dr. Abraham Loeb, not Avi but his colleague at Harvard, who co-authored several papers on interstellar objects, worked with Andrew Quito to model this scenario in detail. Their calculations showed that under plausible assumptions about interior structure specifically, a layered nucleus with CO2-rich outer layers and water-rich deeper layers, with asymmetries in thickness around the nucleus, the kind of abrupt transition seen in 3I Atlas could occur naturally. The timing matches, the spectroscopy matches, the photometric behavior broadly matches, it works. And crucially, this explanation requires no new physics, no exotic mechanisms, no appeal to anything other than well-understood processes that we've seen, albeit in less dramatic form, in solar system comets. Parsimony favours this interpretation. Occam's razor, that guiding principle of scientific reasoning, suggests that when you have two explanations, one involving only known natural processes and one requiring something unprecedented, you should favour the natural one unless the evidence compels otherwise. Most scientists tracking 3I Atlas do favour this explanation. Conversations at conferences, papers submitted to journals, reviews by NASA's Small Bodies Assessment Group, all reflect a consensus that while 3I Atlas is unusual and scientifically valuable, it's a comet. A weird comet, sure. An interstellar comet with compositional and structural properties we're still figuring out. But a comet nonetheless, behaving according to physics we understand, just displaying those behaviors in combinations we haven't seen before, because we've only studied 3 interstellar visitors and our sample size is tiny. NASA spokesperson Tom Statler put it succinctly in a statement released in mid-October. All available evidence points to 3I Atlas being a natural body. It looks like a comet. It acts like a comet. The observed jet behavior, while unusual, falls within the range of phenomena explicable by compositional heterogeneity and thermal evolution. There is no credible basis for alternative interpretations at this time. That statement is careful, measured, and reflects the scientific mainstream. It's almost certainly correct. If you're keeping score, the smart money is on natural explanation, compositional transition, case closed once we get more data to confirm the details. But there's always a but in science, especially when the data are still coming in, and some observations don't fit the model quite as neatly as you'd like. And that but is what keeps researchers like Avi Loeb, yes, the more prominent Avi Loeb, former chair of Harvard's astronomy department, and currently head of the Galileo project Awake at Night. Because while the compositional transition model explains the overall picture, 3 specific observations documented during the reversal period are harder to account for. Not impossible, not definitively ruled out, but harder, requiring auxiliary assumptions, fine-tuning, or appeals to low-probability configurations. And when you're a scientist who has spent your career advocating for taking the search for extraterrestrial technosignatures seriously, who has argued publicly that we should apply the same rigor to looking for alien artifacts as we do to looking for natural phenomena, those 3 awkward data points look less like noise and more like signals worth investigating. Not because they prove anything, but because they suggest questions worth asking. Questions that the mainstream might be inclined to gloss over in favour of the comfortable natural explanation, but questions that, if ignored, might cause us to miss something genuinely important. So let's turn to those 3 observations. Let's examine them carefully, fairly, without prejudging the conclusion. Let's see what's easy to explain and what's hard. And let's be honest about the degree of uncertainty we're dealing with, because uncertainty is where science lives. Certainty is where science dies. This explanation works. Almost. And that almost is where the story gets interesting. Observation number 1. The timing was too precise. The compositional transition model predicts that as a comet approaches the Sun, the thermal wave penetrates progressively deeper, activating different volatile reservoirs as temperatures cross sublimation thresholds. This should be a gradual process. The surface warms incrementally. The subsurface warms more slowly because heat has to conduct through low conductivity ice and rock. The transition from CO2-dominated to water-dominated outgassing should unfold over weeks or even months, not days. You'd expect to see the old jets fading gradually as the new jets ramp up, with an extended overlap period where both volatile species are contributing significantly. What actually happened with 3i Atlas was sharper. The jet reversal occurred within a 10 to 14-day window in mid-October. Before October 5th, the jets were oriented in the original direction, dominated by carbon dioxide outgassing. By October 17th, they had reversed. The transition was fast. Too fast, according to thermal models that assume typical comet nucleus properties like porosity, thermal inertia, and conductivity. Now, you can adjust those parameters, make the nucleus highly porous, increasing its thermal response speed, make it smaller than the brightness suggests, which increases surface area to volume ratio and accelerates warming. Assume that previous outgassing created a network of cracks and vents that allowed the thermal wave to penetrate faster than pure conduction would allow. All of these adjustments are physically plausible. Real comets are heterogeneous. They're not uniform spheres of identical ice. They have structure, voids, variations. Maybe 3i Atlas just happened to have internal structure that made the transition particularly abrupt. But here's the rub. Each adjustment you make to speed up the transition also has other observable consequences. High porosity affects the dust-to-gas ratio in the coma. Small nucleus size affects the total outgassing rate. Crack networks affect the spatial distribution of jets in ways that should be visible photometrically. When you tune the model to match the abrupt timing, you risk mismatching other observables. It's a balancing act, and the balance point requires fairly specific conditions. Not impossible conditions, just specific ones. The kind that make you say, okay, but that's a bit convenient, isn't it? Observation number 2. The directionality was too precise. When a comet transitions from one volatile-dominated regime to another, you'd expect the new jets to be distributed across multiple regions of the nucleus. Water ice isn't concentrated in just one spot. It's part of the bulk composition, distributed throughout, possibly with gradients but not completely segregated. So when water sublimation turns on, you should get multiple jets forming in different locations as different areas heat up and vent. The net effect might shift the overall coma asymmetry, sure, but you'd expect a diffuse distributed pattern. What 3i Atlas showed was more focused. The new jets appeared to be oriented consistently in a single direction, not randomly distributed, not multidirectional, but aligned. Statistical analysis of the coma brightness distribution suggested that the probability of this alignment occurring by chance, given the expected number of active regions, was somewhere between 4 and 6%. Low, but not astronomically low, within the realm of things that happen occasionally. But think about what that means. you're essentially requiring that the water-rich regions of the nucleus, once heated, all happen to be on one side, and that side happen to be oriented such that the jets pointed in the opposite direction from where the CO2 jets had been. That's geometrically possible if the nucleus has strong internal compositional asymmetry. Maybe it's a contact binary, two distinct lobes with different composition, and the transition corresponded to shifting from one lobe's activity to the others. Or maybe it's a single body but with an uneven formation history that left water concentrated in one hemisphere and CO2 in another. Again, you can make it work, but you're adding structure, adding assumptions about how the object formed and how it's put together internally, assumptions that we can't verify directly because we can't see inside the nucleus. We're inferring structure from behaviour, which is fine, that's how science works, but the structure you're inferring is conveniently tailored to explain the observation. It's not independently motivated, it's ad hoc. And when explanations start getting ad hoc, that's when scientists start getting uncomfortable. Not because ad hoc explanations are wrong, they might be right, but because they're less predictive. They're fit to data rather than predict data. They work backwards from observation to mechanism instead of forwards from mechanism to prediction. They're less satisfying epistemologically. Observation number 3. The astrometric residuals were too small. This one's subtle, but important. When a comet jets, the recoil from the ejected mass exerts force on the nucleus. That force, sustained over time, changes the comet's trajectory. These are called non-gravitational accelerations, and they're the reason comet orbits deviate from pure Keplerian ellipses. We measure these deviations astrometrically by tracking the comet's position against the background stars with high precision and comparing the observed motion to the predicted motion from gravity alone. The difference tells you how much non-gravitational force is acting. For 3I Atlas, given the observed brightness of the coma and the dust production rate inferred from that brightness, you can estimate how much gas is being ejected. From the gas mass loss rate, you can calculate the recoil force. From the recoil force and the nucleus mass, you can predict the non-gravitational acceleration. And here's the thing, the predicted acceleration is larger than what the astrometric measurements show. In other words, 3I Atlas is outgassing vigorously, the coma is bright, the jets are active, but the orbit isn't perturbing as much as it should. Either the nucleus is more massive than we think, which would reduce the acceleration for a given thrust, or the jets are somehow balanced, thrusting in opposing directions such that the net force is small, or something else is going on. More massive nucleus? Possible. But mass estimates come from multiple lines of evidence: rotation period, brightness, outgassing rate, assumptions about density. If you make the nucleus significantly more massive, you have to adjust other parameters to keep everything consistent. You end up with a very large, very dark nucleus to explain the brightness, or a very dense nucleus with unusual composition. Each adjustment cascades into other observables. Balanced jets? Also possible. If the nucleus has jets firing in multiple directions that happen to approximately cancel in terms of net thrust vector, the orbital perturbation would be minimized. But achieving near-perfect balance is statistically unlikely unless there's some physical reason for it, like highly symmetric outgassing or some self-regulating mechanism. And if the jet's reversed, the balance would need to be maintained through the transition, which requires the new jets to coincidentally also be balanced. That's another layer of fine-tuning. Individually, each of these 3 observations has plausible natural explanations: abrupt timing, internal structure, precise directionality, compositional asymmetry, small astrometric residuals, massive nucleus or balanced jets. Fine. Science accommodates these explanations. Models are adjusted, papers are written, the mainstream interpretation remains intact. But when you step back and look at all 3 together, a pattern emerges. Each explanation requires invoking specific, somewhat unusual conditions. Each requires 3I Atlas to be not just an interstellar comet, but an interstellar comet with a particular set of internal properties and structural configurations that happen to produce the observed behaviour. And while any one of those configurations is plausible, the combination starts to feel like threading a needle. This is where Avi Loeb enters the conversation, and this is where the discussion shifts from "here's an interesting comet" to "here's an interesting question about how we decide what deserves serious investigation versus what deserves Occam's razor dismissal." Because Loeb looks at these 3 observations and says, there's another explanation that accounts for all 3 simultaneously without requiring fine-tuning. The timing is precise because it's controlled. The directionality is precise because it's aimed. The astrometric residuals are small because the thrust is optimized for minimal orbital perturbation, or because the mass is artificially large due to internal structure we can't see. In other words, what if 3i Atlas isn't entirely natural? What if it's a probe? Most scientists hear that and immediately roll their eyes. Loeb has developed a reputation, especially since his advocacy around 1i/Oumuamua, for being too willing to speculate about alien technology. His colleagues respect his contributions to astrophysics. He's published hundreds of papers on legitimate topics, but worry that his public fascination with extraterrestrial artifacts undermines the credibility of the field. They see 3i Atlas as yet another case where Loeb is pattern matching onto his preferred hypothesis, rather than following where the data most naturally lead. And maybe they're right. Probably they're right. The prior probability of encountering an alien probe in our solar system is extraordinarily low. The prior probability of encountering a weird comet is much higher. When you fold those priors into a Bayesian analysis, the natural explanation wins overwhelmingly unless the data are absolutely screaming artificiality. And the data aren't screaming, they're whispering. Maybe. But here's the thing, Loeb isn't claiming certainty. He's claiming the hypothesis is testable and therefore worth testing. He's arguing that we've built this entire infrastructure for detecting interstellar objects, for characterizing them, for searching for technosignatures, and now we have an object displaying behavior that's at least ambiguous enough to warrant serious scrutiny rather than reflexive dismissal. He's saying, let's look closely, let's gather the data, let's apply rigorous analysis, and let's not let our biases either toward natural explanations or toward exotic ones cloud the investigation. So let's examine his reasoning. Let's see what the controlled maneuver hypothesis actually predicts, how it explains the observations, and what would be required to test it. Not because we're endorsing it, but because understanding it is part of understanding the full picture. And because, at the end of the day, the way science handles controversial ideas when the stakes are this high tells us something about how science works, for better or worse. The jet reversal happened. That's not in dispute. Why it happened is. And that why is about to take us into territory that makes most astronomers deeply uncomfortable, which might mean it's exactly the territory we need to explore carefully. Abraham. Avi Loeb is not your typical astronomer in his public engagement style, but his credentials are unimpeachable. Former chair of Harvard's astronomy department, former head of the Institute for Theory and Computation, former chair of the board on physics and astronomy of the National Academies, author of over 1,000 scientific papers, recipient of numerous awards. He's worked on black holes, early galaxy formation, cosmic reionization, the first stars mainstream, respectable astrophysics. But in recent years, particularly since the discovery of 1i/Oumuamua in 2017, he's become known for something else. His willingness to publicly entertain the hypothesis that some interstellar objects might be artificial. This hasn't made him popular with many colleagues. Science operates on conservatism. You don't claim extraordinary things without extraordinary evidence. You don't speculate wildly in public because it confuses the public and gives ammunition to pseudoscience. You stay in your lane, you do careful work, you publish in peer-reviewed journals, and you let the process work. Loeb has largely followed those norms. His papers are peer-reviewed, his arguments are quantitative, his reasoning is laid out for scrutiny. But he's also willing to talk to the press, to write op-eds, to appear on podcasts, and to frame his ideas in language that explicitly invokes the possibility of extraterrestrial technology. That openness crosses an unwritten boundary in academic astronomy, and it's cost him. But set aside the personality and the sociology for a moment. Let's look at the hypothesis itself. What is Loeb actually arguing about 3i Atlas? The core claim is this: the observations of 3i Atlas are consistent with controlled propulsion, specifically a trajectory correction maneuver executed as the object approached perihelion. The jet reversal wasn't a compositional transition, it was a thruster firing. The timing precision? That's because it was deliberate, activated at a specific heliocentric distance to achieve a specific goal. The directional precision? That's because the thrust was aimed, not randomly distributed. The small astrometric residuals? That's because the maneuver was designed to be subtle, a course correction rather than a dramatic burn, executed by an object with internal mass distribution or propulsion efficiency we don't associate with natural comets. Why would an interstellar probe execute a course correction near perihelion? Loeb offers a few scenarios. 1. The probe is using a gravity assist from the Sun, and the trajectory correction optimizes the outbound velocity or direction for a subsequent target, maybe another stellar system, maybe another object in our solar system. 2. The probe is performing observations and needs to adjust its trajectory to keep certain targets in view or to avoid excessive heating. 3. The probe is demonstrating functionality, essentially signaling that it's operational to any observers who might be paying attention. That third one sounds speculative, bordering on science fiction, and it is speculative. Loeb acknowledges that. But he points out that if you're seriously considering the possibility of extraterrestrial probes, you have to think about what their mission profiles might be. A passive probe, one that simply drifts through the solar system collecting data, might look entirely natural. An active probe, one that adjusts course or modulates its emissions, would reveal itself through behavior that natural objects don't display. The jet reversal, if artificial, would be exactly that kind of reveal. Now, how do you test this? What observations would distinguish controlled propulsion from natural outgassing? Loeb and his co-authors have published papers outlining several signatures. First, trajectory analysis. A natural comet's orbit is perturbed by non-gravitational forces in ways that depend on the comet's rotation, jet geometry, and outgassing rate. Those perturbations should correlate with observable activity. Brighter coma means more thrust. But the relationship is noisy because jets aren't symmetric and rotation is complex. Still, over time, with enough data, you can statistically test whether the observed trajectory perturbations are consistent with random outgassing, or whether they show patterns indicative of optimization, like preferentially targeting specific orbital parameters. Second, spectroscopy. Natural comets outgas volatiles that reflect their formation environment water, carbon dioxide, ammonia, methanol, organic compounds. An artificial object might show spectral signatures that are unusual, anomalous isotopic ratios inconsistent with stellar nucleosynthesis, emission lines from industrial materials like aluminum or nickel in unexpected amounts, or complete absence of organics that should be present. The JWST spectroscopy of 3I Atlas showed nothing obviously anomalous. It looks like a CO2-rich comet, but the spectral coverage wasn't exhaustive, and subtle anomalies might be buried in the data. Third, radio emissions. A functioning probe might emit radio waves, either as communications, as a byproduct of onboard systems, or as active radar sensing. Several radio telescopes have attempted to observe 3I Atlas at multiple frequencies. As of late October 2025, no confirmed radio detections have been reported. That absence is consistent with either a natural object or a probe that's radio quiet, either by design or because it's not currently transmitting. Fourth, acceleration anomalies. If the jet reversal was propulsion, then careful astrometric tracking before, during and after the reversal should show acceleration patterns that don't match the expected photometric behavior. Specifically, if the brightness suggests a certain outgassing rate, but the trajectory perturbation suggests a different thrust magnitude or direction, that's a red flag. The data here are inconclusive. The astrometric residuals are small, which is anomalous in one sense, but within margins of error given uncertainties in nucleus mass and jet geometry. Fifth, timing correlations. Natural processes are driven by solar heating, which is smooth and predictable. If the jet reversal happened at a specific heliocentric distance that corresponds to some orbital mechanic purpose, like maximizing a gravity assist, or aligning with Earth's position for communication or observation that would suggest intentionality. Loeb has noted that 3I Atlas's perihelion occurs during solar conjunction as seen from Earth, meaning we can't observe the object at closest approach. Coincidence? Almost certainly. But if you're pattern matching for intentional avoidance of observation, it's the kind of detail that stands out. Loeb himself has publicly stated that he assigns roughly 30 to 40% probability to 3I Atlas being non-natural in origin. That's shockingly high by conventional standards. Most astronomers would put the probability well below 1%, perhaps below 1 in 1,000. The discrepancy reflects different priors how much weight you give to the possibility of interstellar probes existing and visiting our system in the first place, and different interpretations of how anomalous the data actually are. NASA's response, as mentioned earlier, has been skeptical but not dismissive. Tom Statler's statement emphasized that the object looks like a comet, and that available evidence points to natural origin. But NASA is also tracking 3i Atlas closely. Multiple observatories are coordinating observations. The post-perihelion data, when it arrives in November and December, will be scrutinized carefully. If there are further anomalies, unexplained trajectory changes, spectral oddities, anything that deepens the mystery, the level of scrutiny will increase. The broader astronomical community is split along predictable lines. Researchers focused on cometary science see 3i Atlas as an exciting natural laboratory for studying interstellar comet composition and behavior. They're writing papers on the thermal models, the compositional transitions, the photometric evolution. They see Loeb's hypothesis as a distraction, a sensational claim that generates headlines but doesn't advance the actual science. Researchers in the SETI community and the Galileo project are more open to taking the artificiality hypothesis seriously, not because they think it's likely, but because they think it's important to have rigorous protocols for evaluating such claims when the objects present themselves. There's also a reputational dimension. Astronomers worry that if they take the probe hypothesis too seriously, they'll be tarred as believers or UFO chasers, career-damaging labels in a field that prides itself on empiricism and skepticism. Conversely, SETI researchers worry that if they dismiss anomalous observations too quickly, they'll miss genuine technosignatures and undermine the very mission they're pursuing. It's a damned if you do, damned if you don't situation, and it creates an environment where open discussion becomes fraught. Loeb is aware of this dynamic. He's explicitly stated that his goal is to move the conversation about technosignatures from philosophical speculation to empirical science. He wants observations, data, testable predictions. He wants the field to develop rigorous methods for distinguishing natural from artificial, methods that can be applied dispassionately whenever an ambiguous object appears. He argues that the current approach, assuming natural unless proven otherwise beyond all doubt, effectively guarantees we'll never identify artificial objects even if they're out there, because the bar for proven otherwise is set impossibly high. His critics argue that the bar should be high, precisely because the prior probability is so low and the consequences of crying wolf are so severe. If astronomers start labeling every unusual comet as possibly artificial, the field loses credibility. The public stops trusting scientific statements, funding agencies roll their eyes, the whole enterprise suffers. Better to err on the side of caution, they say, and only invoke artificiality when the evidence is truly overwhelming. Both sides have valid points. This is a genuinely difficult problem in scientific epistemology. How do you calibrate your skepticism when dealing with low probability, high impact hypotheses? How do you avoid both false positives, claiming aliens when it's just nature, and false negatives, dismissing aliens because it's easier to assume nature? There's no perfect answer. The best you can do is be transparent about your reasoning, make testable predictions, gather data, and revise your beliefs as evidence accumulates. Which brings us to the test that's happening right now. 3i Atlas reached perihelion on October 29, 2025. For roughly 2 weeks around that date, the object was too close to the Sun in Earth's sky for ground-based telescopes to observe safely. We're effectively blind. The object is behind the Sun from our perspective, doing whatever it's going to do, outgassing, fragmenting, accelerating, sitting quietly, and we won't know what happened until it emerges. When it does emerge, in early to mid-November, every telescope that can point at it will be pointing at it. The trajectory will be recalculated with fresh astrometry. The brightness will be measured to see if perihelion heating caused a surge or if the object fragmented. Spectroscopy will check for compositional changes. Photometry will map the coma structure to see if the jets are still reversed or if they've shifted again. And all of that data will feed into models, both natural and speculative, and the probabilities will be updated. If everything looks like a normal comet post-perihelion, predictable outgassing, no unexplained accelerations, composition matching thermal models, then the natural explanation wins decisively. Loeb's hypothesis fades into footnote status, and 3i Atlas becomes a scientifically valuable, but ultimately conventional interstellar comet. If the anomalies deepen, if the trajectory changed in ways not explained by outgassing, if new spectral features appeared, if radio emissions are detected, then the investigation intensifies, the mainstream becomes less certain, and the possibility of something extraordinary creeps closer to being taken seriously. The clock is ticking. By the time you're watching this, the critical observations may already be in progress. The data are being gathered, the analysis is underway, and within weeks we'll know more. Not everything. Maybe not even enough to reach a definitive conclusion, but more, and that's how science works. One observation at a time, one test at a time, one hypothesis eliminated or supported at a time, until the truth, whatever it is, becomes clear. But before we get lost in the suspense of waiting for post-perihelion data, we need to zoom out and understand the bigger picture. Because 3i Atlas isn't unique just because of its behaviour. It's unique because of when it arrived. We're living through a revolution in interstellar object detection, a revolution driven by new telescopes, new surveys, and new capabilities. And that revolution means 3i Atlas is likely just the first of many such visitors we'll study in detail over the next decade. Understanding that context changes how we think about this object and what it represents, which is where the story broadens from one mysterious comet to the future of how we explore our cosmic neighbourhood. October 29th, 2025. Mark that date. At approximately 1437, Universal Time, 3i Atlas reached perihelion, its closest approach to the Sun at a distance of 1.356 astronomical units. That's about 203 million kilometres, roughly halfway between Earth's orbit and Mars's orbit. Not particularly close by solar system standards. Some comets graze the Sun's surface, passing within a few solar radii and experiencing temperatures high enough to vaporise rock. 3i Atlas's perihelion is comparatively mild, but it's close enough for solar heating to peak, close enough for any remaining volatile ices to respond dramatically, close enough that if this object is going to reveal its true nature, this is when it happens, and we couldn't watch. Solar conjunction. From Earth's perspective, 3i Atlas passed behind the Sun during its perihelion approach. The geometry was such that the object, the Sun and Earth, formed nearly a straight line, with the Sun in the middle. That means any telescope on Earth or in Earth orbit that tried to observe 3i Atlas during perihelion would have been pointing dangerously close to the Sun itself. You can't do that without risking damage to instruments and blinding detectors. Solar observatories have filters and occulting disks designed to block the Sun's overwhelming light, but they're optimized for observing the Sun's corona, not faint comets hiding in the glare. 3i Atlas effectively disappeared from view for about 2 weeks, from late October into early November. The last good observations before conjunction came in mid-October. That's when the jet reversal was confirmed. The object was brightening as expected from increased solar heating, the jets were active, and the coma structure showed the reversed orientation. Then it slipped behind the Sun, and we went silent. No updates, no new images, just waiting. Now, there are other platforms besides Earth. Mars has orbiters NASA's MAVEN, ESA's Mars Express, others equipped with cameras and spectrometers. Mars was geometrically positioned such that 3i Atlas wasn't behind the Sun as viewed from Martian orbit. In principle, Mars assets could have observed the comet during Earth conjunction blackout. Whether those observations were actually made, and if so, what they showed, hasn't been publicly disclosed as of late October. Data transmission from Mars takes time, processing takes time, and mission priorities for those orbiters are focused on Mars science, not transient comet observation. But the possibility exists that we have data from perihelion that just hasn't been released yet. If so, that data will be gold. It will show whether anything unusual happened at closest approach, whether the comet brightened more or less than expected, whether the jets remained stable or changed again. Assuming we don't have secret Mars data, what do we expect to see when 3i Atlas emerges from conjunction in early November? The natural comet scenario makes specific predictions. First, brightness should have peaked near perihelion and should now be declining as the object moves back out. The heliocentric distance is increasing, solar heating is decreasing, outgassing should taper off. Second, the jet structure should be stable in the new reversed configuration, driven by water sublimation now that the comet is warm enough for water to dominate. Third, spectroscopy should show increased water vapour relative to carbon dioxide consistent with thermal models. Fourth, the orbit should show modest non-gravitational perturbations consistent with the level of outgassing observed photometrically. If all 4 of those predictions are confirmed, the compositional transition hypothesis is strongly supported. The anomalies that looked puzzling in October will resolve into the natural evolution of an unusual, but ultimately ordinary comet. Papers will be published, models will be refined, and 3i Atlas will be catalogued as scientifically interesting but not paradigm-shifting. But what if one or more of those predictions fails? What if the brightness doesn't decline as expected, or worse, increases post-perihelion? What if the jet structure changes again, exhibiting a pattern that can't be explained by rotation and thermal response? What if spectroscopy reveals compositional anomalies that weren't present before new molecular species, isotopic ratios that don't fit stellar nucleosynthesis models, emission lines from elements that shouldn't be outgassing at these temperatures? What if the astrometry shows a trajectory change inconsistent with the observed outgassing, implying either hidden mass or directed thrust? Any one of those outcomes would escalate the investigation. NASA would convene review panels. Observing time on Hubble, JWST, and major ground-based telescopes would be allocated urgently. Radio telescopes would conduct targeted searches for emissions. The data would be scrutinized by independent teams to rule out systematic errors. The Loeb hypothesis, currently a fringe position, would gain traction. Not validation. One anomalous observation doesn't prove artificiality, but enough traction that serious resources would be devoted to testing it rigorously. There's also the possibility of fragmentation. Comets sometimes break apart near perihelion due to thermal stress, tidal forces, or structural weaknesses exposed by outgassing. If 3I Atlas fragmented, we'd see multiple components separating over time, each with its own coma, each following slightly different trajectories. Fragmentation would complicate the analysis. It's harder to track non-gravitational forces when you're dealing with a disintegrating object, but it would also provide a natural explanation for any odd trajectory behavior. A fragmenting comet experiences chaotic forces that can mimic directed thrust if you squint hard enough. Conversely, absence of fragmentation would be notable. If 3I Atlas survived perihelion intact despite the thermal stress, that tells you something about its structural integrity. Natural comets vary widely in strength. Some are rubble piles held together by gravity and ice, fragile enough to disintegrate under their own outgassing. Others are more solid, consolidated bodies that can withstand significant stress. A probe, if that's what this is, would presumably be engineered to survive thermal environments, so intact survival wouldn't be diagnostic of artificiality, but it would at least be consistent with that hypothesis. The post-perihelion observation window extends through November and into December. On December 19th, 2025, 3I Atlas makes its closest approach to Earth, passing at a distance of approximately 0.62 astronomical units, or about 93 million kilometers. That's closer than Mars ever gets to Earth. It's close enough for high-resolution imaging, detailed spectroscopy, and precise astrometry. It's the best opportunity we'll have to study this object before it leaves the inner solar system forever, heading back out into interstellar space on its hyperbolic trajectory. After December, 3I Atlas will fade rapidly as it recedes from both the Sun and Earth. By early 2026, it will be beyond the reach of all but the largest telescopes, and even those will struggle to gather meaningful data. The object will become a distant dot, then a memory, then a line in the catalogue of interstellar visitors. Whatever we're going to learn, we need to learn it in the next 2 months. The timeline for conclusions is longer than the observation window. Raw data come in quickly, but analysis takes time. Astrometric reduction to calculate precise orbits requires weeks of positional data. Spectroscopic analysis involves complex modelling to extract composition from emission and absorption lines. Thermal models need to be run for a range of parameters and compared to photometric light curves. Peer review adds months. So even if something spectacular is observed in November or December, we won't see consensus scientific papers until mid-2026 at the earliest. But preliminary results, informal reports, conference presentations, those will come faster. The astronomical community is watching. Social media is watching. If something genuinely weird is detected, word will leak long before formal publication. And if nothing weird is detected, that information will also spread. The narrative around 3I Atlas will solidify one way or another within weeks, even if the detailed scientific validation takes longer. So here we are, in this window of uncertainty. The object is behind the Sun. The critical observations are about to begin. The outcome is unknown, and whether you're a believer in the probe hypothesis, a skeptic who thinks it's all much ado about nothing, or somewhere in between, you have to admit, this is how discovery works. This is the edge of knowledge. This is the moment when nature decides whether to reveal something mundane or something that changes everything. But regardless of what 3I Atlas turns out to be, It's part of a bigger story, a story about how we're finally developing the tools to find and study interstellar objects routinely, not as rare flukes, but as a regular part of solar system astronomy. And that shift, from 3 objects in 8 years to potentially dozens per year, is about to transform the field in ways that go far beyond any single comet. That transformation is being driven by an observatory that just came online, an observatory that's about to flood us with discoveries, and that observatory is what we need to talk about next because it's the reason 3i Atlas won't be alone for long. Imagine trying to spot a faint, fast-moving object crossing the night sky, an object barely brighter than the faintest stars visible to the naked eye, moving against the background of billions of stars, galaxies, and cosmic debris. Now imagine doing that every night, across the entire visible sky, catching objects that are only briefly bright enough to detect before they fade into obscurity. That's the challenge of interstellar object detection, and until very recently it was nearly impossible. 1I/Oumuamua was discovered almost by accident in 2017 by the Pan-STARRS survey, a telescope in Hawaii designed to find near-Earth asteroids. 2I/Borisov was found in 2019 by an amateur astronomer in Crimea using a homemade telescope. 3i Atlas was detected by the Asteroid Terrestrial Impact Last Alert System in early 2025. All 3 discoveries were serendipitous, luck combined with gradually improving survey capabilities. But luck is about to become systematic. The Rubin Observatory, located on Cerro Pachon in Chile, represents a quantum leap in survey astronomy. Formerly known as the Large Synoptic Survey Telescope, the Rubin Observatory officially began its Legacy Survey of Space and Time (LSST) in early 2025. This is not just another big telescope. It's a purpose-built discovery machine designed from the ground up to image the entire southern sky repeatedly, night after night, generating a movie of the universe that captures anything that changes or moves. The numbers are staggering. The primary mirror is 8.4 meters in diameter, making it one of the largest survey telescopes on Earth. But size alone isn't what makes Rubin revolutionary. It's the field of view. Most large telescopes have narrow fields, seeing tiny patches of sky in exquisite detail. Rubin sees 3.5 degrees across an area equivalent to about 40 full moons. That wide field, combined with a 3,200 megapixel camera, the largest digital camera ever built for astronomy, means Rubin can image huge swaths of sky in single exposures. And it does this fast. Every few nights, the entire accessible sky gets imaged. Every patch of sky is revisited compared to previous images, and any changes are flagged automatically. The system generates approximately 20 terabytes of data every night. That's raw images, processed images, catalogues of detected objects, alerts for anything that moved or changed brightness or appeared where nothing was before. The data pipeline is highly automated because no human team could possibly keep up with the volume. Algorithms identify candidates, asteroids, comets, variable stars, supernovae, transient events. Those candidates are filtered, prioritized, and distributed to follow-up networks within minutes. The entire system is designed for real-time discovery. For interstellar objects, this changes everything. The key signature of an interstellar visitor is its orbit. Natural solar system objects, comets. Asteroids follow elliptical or parabolic orbits bound to the Sun. Interstellar objects follow hyperbolic orbits, unbound, passing through once and never returning. But you can't determine an orbit from a single observation. You need multiple observations over time, tracking how the object moves, fitting the trajectory, calculating the orbital parameters. The faster you get those follow-up observations, the more accurate the orbit determination, and the sooner you know whether you're looking at something interstellar. Rubin's rapid cadence means interstellar objects will be detected earlier in their approach, giving more time for follow-up. Its sensitivity means fainter objects, smaller bodies, or objects further away will be found. And its systematic coverage means fewer objects will slip through unnoticed. Current estimates suggest Rubin will detect between 1 and 2 interstellar objects per year on average, possibly more if the true population density in interstellar space is higher than models predict. Over a decade, that's dozens of visitors, a statistical sample large enough to characterize the population, to understand what's typical and what's unusual, to test whether objects like 3i Atlas are rare anomalies or common variants. This population statistics approach is crucial for the artificiality question. If every interstellar object behaves oddly in unique ways, That suggests natural diversity comets are just weird, and interstellar comets are weirder because they formed in different environments. But if patterns emerge if certain objects cluster in particular orbital characteristics, or display similar anomalous behaviours, or show correlations between composition and trajectory that's more interesting, patterns might indicate selection effects, or they might indicate something else. A fleet of probes, for instance, might have characteristic velocity distributions or preferential targets within the solar system. Natural objects should be more random. Rubin also enables better characterization, because it images in multiple filters U, G, R, I, Z, Y bands covering near ultraviolet through near infrared. It can measure colors. Colors tell you about surface composition and scattering properties. Combining Rubin's photometry with spectroscopic follow-up from other telescopes gives a complete picture of each object's physical properties. And because Rubin will observe each object multiple times over its visibility window, we'll get rotation periods, phase curves, outburst timing, all the photometric details that reveal internal structure and activity. There's also the early warning benefit. If Rubin detects an interstellar object years before perihelion, while it's still in the outer solar system, there's time to plan missions. Not intercept missions, those require decades of advance notice to be feasible with current propulsion, but intensive observation campaigns, coordinate space telescopes, schedule radio observations, arrange for spectroscopy at the world's best facilities, maybe even deploy small spacecraft already in the outer solar system, like Voyager or New Horizons, to observe from different vantage points if the geometry works. Early detection turns reactive astronomy into proactive astronomy. Of course, challenges remain. Rubin will find thousands of new moving objects every night. Most will be main belt asteroids, near-Earth objects, Kuiper belt bodies solar system locals. Distinguishing interstellar visitors from the background requires orbit determination, which requires follow-up, which requires coordination. The alert system needs to prioritize candidates effectively, so that the most interesting objects get attention before they fade. False positives, objects that initially look hyperbolic, but turn out to be highly eccentric ellipses, will consume telescope time. The system will learn, algorithms will improve, but there will be growing pains. There's also the question of how the community responds when Rubin finds something genuinely anomalous. If 3i Atlas-like events become common, does the field develop standardized protocols for evaluating artificiality? Do we establish threshold criteria, spectral signatures, trajectory patterns, radio emissions that trigger escalated scrutiny? Or does each case remain ad hoc, debated individually, subject to the same sociological tensions that are playing out around 3i Atlas right now? The infrastructure for detection is being built. The infrastructure for interpretation is still improvised. But the potential is enormous. Imagine 10 years from now. Rubin has been operating for a decade. We've detected 50 interstellar objects, characterized their orbits, measured their compositions, tracked their outgassing. We have a catalogue. We know what's typical, mostly CO-rich comets like 3i Atlas, occasional rocky bodies like Oumuamua, size distributions, velocity distributions, orientation distributions. And in that catalogue, outliers stand out. Objects that don't fit the natural distribution, that show correlated anomalies, that maybe, just maybe, hint at intentional design. Or alternatively, the catalogue shows that 3i Atlas was unusual but not unique, that interstellar comets are diverse, that they do weird things, that our models based on solar system comets were too narrow, and that's valuable too. Negative results are results. Confirming that we're not seeing probes is part of the scientific process. SETI searches have been running for decades without success, and that non-detection tells us something about the prevalence of technological civilizations, or at least their radio loudness. A decade of Rubin data showing no techno-signatures would tell us something similar. The point is, we're moving from anecdotes to statistics. From here's a weird object, what is it? To here's a population of objects, what are the distributions? And that's how you answer big questions. Not with one dramatic discovery though, that would be nice, but with systematic surveys, large samples, rigorous analysis. Rubin is the tool that enables that approach for interstellar objects. It's the reason the next decade of solar system astronomy will look fundamentally different from the last. But finding the objects is only step one. Once you've found them, you need to characterize them. And for that, you need spectroscopy. You need to know what they're made of, what isotopes are present, what molecules are outgassing, what that tells you about formation conditions and thermal history. You need chemistry. And for faint, fast-moving targets, there's really only one facility capable of delivering the spectroscopic detail required, the James Webb Space Telescope. And that brings us to the role JWST is playing and will continue to play in unraveling these mysteries, because without its infrared eyes, objects like 3I Atlas remain enigmatic dots, instead of characterized visitors. There's a scene that plays out in countless detective stories. The forensic scientist examines a sample, runs it through analysis, and declares, "The chemical signature is unique, I know exactly where this came from." That's spectroscopy in a nutshell. Light carries information. When atoms and molecules absorb or emit light, they do so at specific wavelengths determined by their quantum structure. Every element, every molecule has a unique spectral fingerprint. Observe that fingerprint and you know what you're looking at. For comets, spectroscopy reveals composition. The coma, the cloud of gas and dust surrounding the nucleus, glows in specific wavelengths. As sunlight excites molecules and they re-emit photons. Different molecules emit at different wavelengths. Water vapor has characteristic lines in the infrared and ultraviolet. Carbon dioxide has strong features in the infrared. Carbon monoxide, ammonia, methane, hydrogen cyanide, formaldehyde, each has its own pattern. Point a spectrometer at a comet, collect enough light, and you can inventory what's outgassing. You can measure relative abundances. Is this comet 90% water and 10% CO2, or the reverse? You can even measure isotopes. Is the water enriched in deuterium, suggesting formation in a very cold environment, or is it isotopically normal? For interstellar objects, spectroscopy is doubly important. Not only does it tell you composition, but it tells you about the formation environment of a distant stellar system. If an interstellar comet is enriched in carbon monoxide relative to solar system comets, that suggests it formed farther from its parent star or around a star with different chemistry. If the isotopic ratios are unusual, that might indicate exposure to different stellar radiation environments or formation from molecular clouds with different enrichment histories. Spectroscopy turns interstellar objects into messengers carrying chemical information from across the galaxy. Enter the James Webb Space Telescope. JWST, humanity's most powerful space telescope, is optimized for infrared wavelengths specifically, near-infrared and mid-infrared, roughly 0.6 to 28 microns. Infrared is ideal for comets, because many key molecules have strong emission and absorption features in the infrared. It's also ideal for observing faint, cool objects, because infrared light penetrates dust better than visible light. A comet's nucleus, often obscured by its own coma, becomes more transparent in the infrared, and JWST's enormous 5-meter segmented mirror collects enough light to study targets that would be too faint for most other facilities. In late September and early October 2025, JWST observed 3I Atlas as part of a coordinated campaign involving multiple telescopes. The observations used JWST's near-infrared spectrograph NIRSPEC to capture medium-resolution spectra of the coma. The data were processed, calibrated, and analysed by a team of cometry scientists, and the results were made public in mid-October through a NASA briefing and a preprint paper submitted to the Astrophysical Journal. The headline finding: carbon dioxide dominates the coma, accounting for approximately 87% of the detected molecules by number. Water vapor is present at around 8%. Carbon monoxide is about 3%. Minor species carbonyl sulfide, hydrogen, cyanide, methanol make up the remaining 2%. This is a high CO2 composition, much higher than typical solar system comets, which are usually water-dominated, but it's not unprecedented. Some Oort cloud comets show elevated CO2, and models of interstellar space predict that objects forming in very cold outer regions of stellar systems would naturally be CO2-rich. The isotopic ratios were measured for a few key species. Deuterium to hydrogen ratio in water vapor was slightly elevated compared to Earth's oceans, but within the range seen in solar system comets. Carbon isotope ratios 12C to 13C were also normal. Oxygen isotopes showed no significant anomalies. In other words, the spectroscopy was consistent with a comet that formed naturally in a cold stellar environment, composed of ices that condensed from a molecular cloud, with chemistry similar to the solar nebula. Nothing in the spectra screamed artificial. No unexpected alloys, no industrial compounds, no exotic isotopic signatures that would require non-natural processing. There were claims circulating on social media, always social media, that JWST had detected unusual nickel emission lines, or that certain organic molecules present in the coma were inconsistent with natural formation. These claims appear to be either misinterpretations of the data or outright fabrications. The official analysis, subjected to peer review and scrutiny, shows nothing of the sort. Nickel is sometimes detected in comets, liberated from dust grains as they're heated, but the amounts are trace level and entirely consistent with refractory material formed in stellar environments. The organics detected are simple molecules, hydrogen cyanide, formaldehyde common in molecular clouds and in solar system comets. So spectroscopy supports the natural comet hypothesis. But it doesn't rule out artificiality entirely. A sufficiently advanced probe might be coated in natural material, might outguess Cumtree volatiles deliberately as camouflage, might be engineered to mimic natural spectra precisely. That's unfalsifiable speculation, of course, if you allow for arbitrarily sophisticated mimicry. No observation can definitively rule out artificiality. But it's worth noting that the spectroscopy doesn't provide positive evidence for artificiality. It's negative evidence against the idea that 3i Atlas is obviously artificial. The spectroscopic capabilities of JWST will be critical for future interstellar objects as well. Every visitor that Rubin finds, and that's bright enough, will be queued for JWST observation. Over time, we'll build a spectroscopic library of interstellar comet compositions. We'll see whether they cluster in composition space or span a wide range. We'll test predictions from planet formation models about volatile abundances in different stellar environments. We'll look for correlations between composition and trajectory. Do CO2-rich comets come from particular directions, or particular stellar populations? And if we ever do encounter an object with genuinely anomalous spectroscopy, something with isotopic ratios that don't fit stellar nucleosynthesis, or with molecular species that require high temperatures or unusual chemistry to form JWST, will be the instrument that catches it. That's the power of spectroscopy. It's objective, it's quantitative, it's hard to fake or misinterpret if done carefully. Chemistry doesn't lie, there are limitations of course. JWST's observing time is precious and oversubscribed. Hundreds of programs compete for time, from exoplanet studies to galaxy evolution to cosmology. Comets are a small part of the mission. Each interstellar object gets limited observing hours, enough for basic spectroscopy, but not exhaustive characterization. There's always a trade-off between breadth observing many objects briefly, and depth observing one object extensively. The community has to make those choices based on what's scientifically most valuable. Brightness matters too. JWST can observe faint objects, but not infinitely faint. If an interstellar object is detected early at large heliocentric distance, before it's outgassing significantly, it might be too faint for spectroscopy. You have to wait until it's active, which means waiting until it's closer to the sun, which reduces the time available for observation before it swings back out. Timing is critical. Miss the window, and the object fades beyond reach. Still, the combination of Rubin finding objects and JWST characterizing them is transformative. It's a pipeline. Discovery feeds into follow-up, follow-up generates data, data refine models, models make predictions, predictions guide future observations. It's how astronomy makes progress. And it's why, even if 3i Atlas turns out to be entirely natural, the infrastructure being built right now will serve us well for decades. We're not just studying one comet, we're establishing the framework for studying a population. But understanding what we're seeing requires more than just data. It requires grappling with how science handles controversial ideas, how the community decides what's worth investigating versus what's worth dismissing, and how reputations and careers shape the questions we ask. The 3i Atlas debate isn't just about a comet. It's about the sociology of science, the psychology of belief, and the protocols we use to separate signal from noise when the stakes are existential. And that meta-question, how we know what we know, and how we decide what's worth taking seriously, is what we need to explore next, because it's central to understanding not just this case, but every case like it that will follow. Science has a funny relationship with mavericks. On one hand, progress often comes from people willing to question orthodoxy, to propose ideas that sound crazy until evidence vindicates them. Plate tectonics was ridiculed before it was accepted. The Big Bang was dismissed as speculative nonsense until cosmic microwave background radiation was discovered. Bacterial origins of ulcers laughed at until proven correct, earning a Nobel Prize. History is full of examples where the maverick was right and the establishment was wrong, and those stories are taught to students as lessons about keeping an open mind. On the other hand, for every maverick who was right, there are hundreds who were wrong. For every Wegener proposing continental drift, there are countless forgotten scientists who proposed theories that sounded revolutionary, but turned out to be nonsense. The base rate matters. Most unconventional ideas fail. Most challenges to established paradigms collapse under scrutiny. Science is conservative by design because conservatism works. It filters out the noise. It protects the field from chasing every wild speculation. It demands extraordinary evidence for extraordinary claims, and that demand is a feature, not a bug. Avi Loeb exists in this tension. He's not a crank. His credentials are impeccable. He's contributed to mainstream astrophysics for decades. But his public advocacy for taking the extraterrestrial technosignature hypothesis seriously not as fringe speculation, but as a legitimate scientific question deserving rigorous investigation, has made him controversial. Some colleagues admire his willingness to think boldly. Others worry he's damaging the field's credibility by lending scientific authority to ideas that belong in science fiction, not peer-reviewed journals. The controversy crystallized around 1I/Oumuamua, the first detected interstellar object, discovered in October 2017. Oumuamua was strange. It was elongated, tumbling, red-coloured, and most bizarrely it accelerated away from the Sun in a way that couldn't be explained by gravitational forces alone. Non-gravitational acceleration isn't unusual for comets. That's the rocket effect we discussed earlier, but Oumuamua showed no signs of outgassing. No coma, no tail, no spectroscopic detection of volatiles, yet it accelerated anyway. Loeb and his postdoc Shmuel Bialy published a paper in 2018 suggesting that Oumuamua's acceleration could be explained if the object were a light sail, a thin, reflective structure propelled by radiation pressure from the Sun. Light sails are a real concept, explored for interstellar propulsion by organizations like Breakthrough Starshot. If Oumuamua were a light sail, its unusual shape and acceleration would make sense, and if it were a light sail, it might be artificial. The paper was peer-reviewed and published in the astrophysical journal Letters. It framed the light sail idea carefully as one possible explanation among others, but Loeb's subsequent public comments, interviews, and a popular book Extraterrestrial, the first sign of intelligent life beyond Earth, went further, arguing that the artificial hypothesis should be taken seriously and that the scientific community was irrationally dismissive. The backlash was swift. Other astronomers criticized the hypothesis as insufficiently supported by data, pointing out that natural mechanisms outgassing of hydrogen, sublimation of nitrogen ice could explain the observations without invoking aliens. They accused Loeb of publicity seeking, of lowering the evidentiary standards for claims about extraterrestrial intelligence, and of conflating possible with probable. The debate became heated, sometimes personal, and it coloured how Loeb's subsequent work on interstellar objects has been received. Fast forward to 3I Atlas. When the jet reversal was observed, Loeb was among the first to publicly note the anomalies and suggest that the artificiality hypothesis deserved consideration. For many astronomers, this felt like déjà vu, Loeb once again jumping to aliens when natural explanations were available. For Loeb's supporters, it felt like the community once again reflexively dismissing a legitimate question because of discomfort with the implications. The sociology here is complex. Science is supposed to be objective data or data, and conclusions follow from data regardless of who proposes them. But science is done by humans, and humans are social creatures. Reputation matters. If someone has a track record of making bold claims that don't pan out, their future claims are taken less seriously. Conversely, if someone has a track record of being right, their claims carry extra weight. Loeb's track record is mixed. He's been right about many things in mainstream astrophysics. He's been arguably premature about technosignatures, or at least that's the perception. There's also a reputational risk for the field. Astronomy competes for funding with other sciences. Public perception matters. If the public starts associating astronomy with alien speculation, if every unusual comet generates headlines screaming alien probe, then the field's credibility suffers. Funding agencies, policymakers, the educated public who support science, all need to trust that astronomers are being rigorous, not sensational. And that trust is fragile. Loeb's counterargument is that the risk of missing a real techno-signature because we're too afraid of looking foolish is greater than the risk of occasional false alarms. He argues that the prior probability of extraterrestrial civilizations existing is not negligible. SETI has been searching for decades, which implies that the hypothesis is scientifically respectable, and that if civilizations exist, they might send probes, and if they send probes, some might pass through our solar system, and if that happens, we better be ready to recognize them. He accuses the mainstream of motivated skepticism, where the discomfort of the conclusion drives rejection of the evidence rather than the evidence driving the conclusion. Both sides have valid concerns. The mainstream is right that extraordinary claims require extraordinary evidence, and that we shouldn't invoke aliens prematurely. Loeb is right that we shouldn't reject hypotheses just because they're uncomfortable, and that we need clear criteria for what would constitute sufficient evidence. The problem is that agreeing on those criteria is hard. Consider what would constitute extraordinary evidence for an artificial interstellar object. Radio transmissions, definitely, if confirmed and clearly artificial in structure. But absence of radio doesn't rule out artificiality. A probe might be silent. Anomalous chemical composition? Possibly, but you'd need to rule out natural processes, and nature is creative. Trajectory inconsistent with natural forces? Maybe, but orbital dynamics are complex, and measurement uncertainties leave room for interpretation. Visible structure, like solar panels or antennas. That would be definitive, but requires high-resolution imaging that we can't achieve for fast-moving distant objects. The honest answer is that unambiguous proof would require either incredibly blatant signals like a radio message saying, "Hello, we're aliens," or close-range inspection by a spacecraft, which is currently impossible for interstellar objects passing through quickly. Anything short of that leaves a room for debate, and that means we're stuck in a regime where reasonable people can look at the same data and reach different conclusions based on how they weight prior probabilities and how they interpret ambiguous evidence. This isn't a flaw in science, it's a feature. Science is supposed to be a process of hypothesis testing, model refinement, and updating beliefs as data accumulate. Disagreement is part of that process. Controversy can be productive if it drives better observations and more rigorous analysis. The danger is when controversy becomes tribalized, when people choose sides based on identity rather than evidence, when disagreement turns into dismissal, when the goal shifts from finding truth to winning arguments. There are signs that the 3i Atlas debate is avoiding the worst of that tribalization. Most astronomers, even those skeptical of Loeb's interpretation, agree that 3i Atlas deserves close study. Observing time is being allocated, papers are being written, data are being shared, the process is functioning. That's good. It means the system has resilience that despite personal tensions and reputational concerns, the commitment to empiricism is holding. But there's also a lesson here about how science communicates with the public. When scientists disagree publicly, especially about something with existential implications like alien probes, the public sees mixed messages. Some people conclude that science is unreliable, that experts don't know what they're talking about, that it's all just opinion. Others latch onto the most sensational interpretation, ignoring nuance. Science communicators, journalists, educators, scientists engaging with the public have a responsibility to convey not just the findings, but the uncertainty, the process, the fact that debate is how science works. Loeb has been accused of violating that responsibility, of speaking too confidently about speculative ideas in public forums, where qualifications get lost. His defense is that he's being transparent about his reasoning, that he always includes caveats, that the media often strips nuance, but that's not his fault. There's truth on both sides. Science communication is hard. Balancing honesty about uncertainty with avoiding false balance, balancing bold ideas with responsible caveats, balancing public engagement with professional restraint, these are genuinely difficult challenges. What's clear is that as interstellar objects become more common, the field needs clearer protocols. SETI has protocols for what to do if a candidate signal is detected. Verify independently, rule out terrestrial sources, quantify significance, only then make announcements. Maybe interstellar object research needs analogous protocols. Thresholds for when an object is flagged for intensive follow-up. Criteria for when the artificiality hypothesis graduates from technically possible to worth serious investigation. review panels that evaluate claims dispassionately before they hit the media. This isn't about silencing speculation. It's about channeling it productively. Science thrives on speculation, that's where hypotheses come from, but it also thrives on discipline, on testing before concluding, on proportion between claim strength and evidence strength. Finding that balance, especially in real time with public scrutiny, is an evolving challenge. And it's a challenge that's about to get more intense, because we're not just talking about one comet anymore. We're talking about a future where interstellar visitors are routine, where each one is a test case, where patterns might emerge or might not, and where the question, are we alone? Transitions from philosophical musing to empirical investigation. The infrastructure is in place, the tools are ready, the objects are coming, and the way we handle them, starting with 3i Atlas, sets precedent for everything that follows. Which brings us to the final question. What happens if the answer is yes? Not for 3i Atlas specifically, it's almost certainly a comet, but for some future visitor. What if one of them, someday, turns out to be genuinely, unambiguously artificial? What would detection of extraterrestrial technology in our solar system actually mean? Practically, scientifically, philosophically, how would it change things? And are we ready for that? Not just technologically, but socially, intellectually, emotionally? That's the question we need to grapple with to understand what's really at stake in investigations like this one, and that's where we're heading next. Let's think through the scenario. Not for 3i Atlas, the odds are vanishingly small, and the evidence doesn't support it, but for some future interstellar object detected by Rubin, characterized by JWST, tracked by multiple observatories, and found to display behavior that resists natural explanation. Radio emissions detected at non-natural frequencies, trajectory changes inconsistent with outgassing, spectroscopic signatures of processed materials, structural features visible in high-resolution imaging, geometric shapes, reflective surfaces, modular components, evidence accumulating to the point where the artificiality hypothesis becomes not just plausible, but likely. What then? First, verification. The astronomical community would demand independent confirmation from multiple facilities. The data would be scrutinized for systematic errors, instrumental artifacts, and processing mistakes. Adversarial peer review would be employed teams specifically tasked with debunking the claim, finding alternative explanations, stress testing every assumption. This is how science responds to extraordinary claims. Healthy skepticism isn't denial, it's quality control. If the claim survives that gauntlet, if independent teams reach the same conclusion, if the evidence withstands every challenge, then you move to the next phase. Publication. The findings would be published in major journals Nature, Science, the Astrophysical Journal. Press conferences would be held, coordinated through international organizations like the International Astronomical Union. NASA, ESA, other space agencies would issue statements. The announcement would be carefully worded, emphasizing what is known, what is uncertain, and what further observations are planned. The goal would be to inform the public accurately without sensationalizing, to convey the significance without triggering panic or wild speculation. But let's be honest, control over the narrative would be limited. The discovery of extraterrestrial technology would be the biggest news story in human history. It would dominate global media, social media would explode, conspiracy theories would proliferate, religious communities would grapple with theological implications, governments would be asked to respond, the scientific community's carefully worded statements would compete with clickbait headlines, speculative documentaries, and political opportunism. Managing that information ecosystem would be a monumental challenge. Geopolitically, questions would arise immediately. Who owns the discovery? If a US facility detected it, does the US have a special claim? Of course not. Legally, space is global commons, but politically, tensions could emerge. Would data be shared openly, or would some nations attempt to classify findings for strategic reasons? History suggests international cooperation is possible. Look at SETI protocols, which emphasize transparency, but history also shows that competition and secrecy are human defaults when stakes are high. There are existing frameworks. The United Nations Committee on the Peaceful Uses of Outer Space, COPUOS, has discussed protocols for contact scenarios. CT Research has the Declaration of Principles Concerning Activities following the detection of extraterrestrial intelligence. a non-binding agreement emphasizing openness and consultation. But these are guidelines, not enforceable treaties. In practice, response would be improvised, negotiated in real time, subject to the political climate at the moment of discovery. Then there's the question of communication. If the object is artificial, is it communicating? Is it receiving? Do we attempt to signal it? That decision would be fraught. Some would argue we should observe silently if it's a probe, maybe it hasn't noticed us, and revealing ourselves could be dangerous. Others would argue that if it's in our solar system it probably knows we're here already, and attempting communication is scientifically valuable and ethically appropriate. SETI has long debated whether active SETI transmitting signals into space rather than just listening is wise. Discovering an actual object in our backyard would force that debate from theoretical to urgent. Scientifically, the implications would be profound. Confirmation of extraterrestrial technology answers one of humanity's oldest questions. Are we alone? The answer would be no. And that answer cascades into other questions. Where did the probe come from? How old is it? How advanced is the civilization that built it? Is that civilization still extant, or did they die out long ago, leaving their probes as archaeological relics? Are there many such civilizations, or is this one rare survivor? The Fermi paradox, the tension between the high probability of extraterrestrial civilizations existing and the lack of evidence for them, would be resolved in one direction. They exist, or at least they existed. The question shifts from where is everybody to why haven't we seen them more clearly? Maybe probes are rare. Maybe most civilizations don't build them. Maybe interstellar travel is harder than we think, so even civilizations that try only send a few probes, and we're lucky to catch one. Or maybe probes are common, we've just started looking, and now that we have the tools, we'll start finding more. That last possibility is tantalizing and terrifying. If one probe, why not many? If we've detected one, how many have passed through unnoticed before we had the technology to find them? Are there probes in our solar system right now, dormant, waiting? Are some of the asteroids we've catalogued actually ancient artifacts? That sounds like science fiction, but once you confirm one artificial object, the hypothesis space expands. You have to start checking. Philosophically, the impact would be immense. Human exceptionalism, the idea that we're special, central, unique, would take a hit. We'd be confronted viscerally with the reality that intelligence and technology arose elsewhere, independently, that we're not the pinnacle of cosmic evolution but one instance among potentially many. For some, that would be humbling in a positive way, a cosmic perspective shift that reframes petty human conflicts as trivial. For others, it would be destabilizing, undermining worldviews built on human centrality. Religions would respond in varied ways. Some theologies easily accommodate extraterrestrial life. God created a vast universe. Why wouldn't he populate it? Others would face challenges. Are aliens subject to the same spiritual laws? Do they have souls? Did Christ's sacrifice apply to them, or do they have their own covenants? These aren't questions with easy answers, and different communities would navigate them differently. History suggests that major worldview challenges are absorbed over time, reinterpreted, integrated. But the process isn't always smooth. There's also the question of missions. If we confirm an interstellar object is artificial, can we send a spacecraft to intercept it? The answer depends on trajectory and timing. Interstellar objects move fast tens of kilometers per second. Catching up requires enormous delta V velocity change, which requires either huge amounts of propellant or advanced propulsion like nuclear engines or solar sails. Current technology couldn't intercept something like 3I Atlas on short notice. But if Rubin detects an artificial object years before Perihelion, there might be time to plan a mission. Not easy, not cheap, but possible. Such a mission would be humanity's highest scientific priority. Imagine a spacecraft reaching an alien probe, imaging it up close, analysing its structure, possibly even touching it, sampling it. The data would be priceless. Engineering details could reveal alien technology, materials science, energy systems. Even if we couldn't understand everything, we'd learn, and the symbolic significance humanity reaching out to touch something made by another intelligence would be profound. But let's inject realism. The scenario we're describing, unambiguous detection, clear artificial signatures, global coordination, successful mission, is optimistic. More likely, if we ever do find something artificial, it will be ambiguous. evidence strong but not definitive, debate lasting years, missions proposed but not funded, political gridlock, media frenzy fading as attention spans move on, incremental progress mixed with frustration. That's usually how history works. Messy, slow, complicated, and most likely of all, we don't find anything artificial. Rubin operates for a decade, finds 50 interstellar objects, all natural. Comets, asteroids, ice balls, weird but explicable. SETI searches continue, still silent. The Fermi paradox remains unresolved. We're left with the same question we've always had, just with more data confirming that if they're out there, they're not obviously visiting. That outcome is scientifically valuable too. It would tell us that interstellar travel is rare, or that civilizations don't send probes, or that we're in a quiet region of the galaxy, or that advanced civilizations are more subtle than we imagine. Negative results constrain theories. They're not failures, they're data. So where does this leave us with 3i Atlas? By the time you're watching this, the post-Perihelion observations are likely underway or completed. Preliminary results may already be circulating. The trajectory has been recalculated. The brightness evolution has been measured. Spectroscopy has been taken. And based on those results, the narrative is solidifying. Most probable outcome, 3i Atlas is confirmed as a natural comet with unusual but explicable behaviour. The compositional transition model is validated. The jet reversal is understood as a consequence of internal structure and thermal evolution. Papers are published. Loeb's hypothesis remains a footnote, an interesting speculation that didn't pan out. The object fades into obscurity. Scientifically interesting but not revolutionary. Less probable, but possible. Anomalies persist post-perihelion. The data don't fit natural models cleanly. Questions remain. Investigation continues. The hypothesis space stays open. No definitive conclusion, just ongoing study and debate. Very improbable. Unambiguous evidence of artificiality emerges. The object does something that natural physics can't explain. The paradigm shifts. History pivots. Whatever the outcome, 3i Atlas has reminded us of something important. We live in a universe that's larger, older, and more mysterious than we can fully comprehend. We've built tools, telescopes, spectrometers, algorithms that let us explore that universe in ways previous generations couldn't imagine. And those tools are revealing that our solar system isn't isolated. It's part of a galaxy, a cosmic ecosystem where objects migrate between stars, where the boundary between ours and theirs is porous, where every visitor is a message from deep space and deep time. Whether those messages are natural or artificial, they're worth reading. Every comet tells a story about stellar systems, planet formation, the distribution of volatiles in the galaxy. Every trajectory reveals gravitational dynamics, the architecture of planetary systems, the history of stellar encounters, and maybe one of them will tell a different story, a story of intention, of engineering, of another mind reaching across the void. We're listening now, we're watching, and we're ready scientifically, if not yet emotionally or socially, to hear whatever the universe has to say. 3i Atlas, whether it's a comet or something more, is teaching us how to look, and that might be its greatest gift. So here's what I need from you. First, if this investigation into 3i Atlas has expanded your sense of what's possible out there, hit the like button. It tells the algorithm that deep, evidence-based explorations matter, not just clickbait. Second, drop a comment with your probability estimate. What percentage chance do you give that 3i Atlas is artificial? I'm at about 5%, down from 10% before the spectroscopy data came in. Tell me where you stand and why. Third, subscribe and hit notifications, because between now and December 19th, new data will drop. Post-perihelion observations, trajectory analysis, maybe even Mars orbiter images if we're lucky. I'll be covering every development as the story unfolds in real time. And finally, share this video with someone who still looks up at the night sky and wonders what else is out there. Because every interstellar visitor is a messenger from deep time and deep space. And if we're patient, rigorous, and brave enough to follow the evidence wherever it leads, one of them might finally answer the oldest question humanity has ever asked. Until next time, keep watching the skies.